In this video lecture, we will define the integral of non-negative extended Borel functions using what we saw already in the previous video lecture, which was the integral of simple random function defined by an explicit form. And this is the definition. We have a non-negative extended Borel function f, and then we consider simple random functions g, which are also non-negative, below f, and we compute the integral of those that we know already because we have defined this in the previous video lecture. These are simple measurable functions. And now we take the supremum over all possible choices of simple random variables or simple measurable functions that stay below f. And by definition, so this is the definition of the integral of a non-negative extended Borel function. And we can think of it in a picture. It would be if we have a function like this, then we approximate its integral. This is very different from the Riemann integral. We approximate its integral by taking functions which are simple and are below our function f. So if this would be the function f, in blue, I'm computing here the integral of some simple function, but the simple function itself, if we want, it would be this function here. It is constant, and it is constant, constant. This would be the simple function itself, and well, more like this. So this simple function, which is below f, we compute its integral, and we take the supremum over all possible choices. So this is very different from Riemann integral again, because we don't allow the approximating function, the approximating rectangles, to go above the graph of f. And this is why we see so constantly in all of measure theory that things work well when we approximate from below, but maybe not when we approximate things from above. So let me state the theorem. We'll prove it by bits. Today, just a few bits of this theorem. It's that this definition, it satisfies the axioms of the very first video lecture that we gave last week. The very first thing that we have in this chapter of the lecture notes is that we can define something that we call integral of non-negative extended Borel functions against a certain measure, with respect to a certain measure, and that this definition is linear, unitary, monotone, and sigma additivity. These were axioms, but now they are theorem because we defined explicitly, if we allow supremum to be considered as something explicit. We defined explicitly what the integral is, and now we're going to prove that it satisfies those axioms. So we don't need those axioms anymore. We're actually constructing that integral. One remark that is important to make is the following. We are expanding our space, the space of functions that we can integrate. We started with simple functions. Now we have non-negative extended Borel functions. And then with this definition, we saw that already, we can use it by separating positive and negative parts. We can use it for the general extended Borel functions. But each time we extend, we need to make this remark that according to this definition, if a function is non-negative and also simple, so it belongs to these two spaces, it is simple and non-negative, then how do you compute its integral? Do you use the previous definition or do you use this new definition? And it turns out it doesn't matter which one you use, it will give the same number. And that is simply because if f is simple, the supremum here will be achieved or will be attained by taking g equal f. And then by monotonicity, of course, you cannot go above f. And since you can get a function that is equal to f, then the supremum will be the integral of f. So this definition is consistent with the previous definition. So the first property to prove is that it's monotone, which is stated here if f is a non-negative extended Borel function and g is another non-negative extended Borel function that is larger than f for every point, then the integral of g will also be larger than the integral of f. And for the proof, we don't need to write anything. We just need to come back here. Okay, so if we have f, so let's, for the purpose of this theorem, let's put age here. So if we have f here or g, and we're assuming g is larger than f, so we have some g larger than f, so this supremum is taken over a certain family of functions, age, when we plug in f here. Now, if instead of f, we plug in some g, which dominates f, then the family increases. So maybe we are adding new functions age here to the set that will still satisfy this condition when we replace f by g. So simply because this set here can increase, the supremum can increase, but it cannot decrease. Yes, or in other words, what we are using here is that the supremum of a set is smaller than the supremum of another set if the set is a subset of the other one. And so just this alone gives us monotonicity. And now finally, let us prove monotone convergence. You will remember that in some 3 video lectures before, we stated the monotone convergence theorem, but then we proved it. We proved it using the axiom that there exists an integral and that the integral is sigma additive. The problem is we now want to prove that this integral satisfies the axioms, so we want to prove that it's sigma additive. We cannot use it yet, and we're going to do the other way around. We're going to prove monotone convergence and use it to prove sigma additivity. And of course, when we are proving monotone convergence, we cannot use sigma additivity because this will be circular. So we don't want to have a circular argument, so we have to prove monotone convergence really by hand using our brute force. So I think it's a good time to take a break. And the second part of this video lecture, we're going to give the proof of monotone convergence.